So in this video, we are going to talk about the structure of ionic compounds. So to start off with, we need to know, or you need to know, that ionic compounds are commonly known as salts. So I know that the most common salt that you've heard of, table salt, usually when you hear the word salt, you think of sodium chloride, table salt. But salt to scientists is actually a very generic term for ionic compounds. Okay, so now if you think about it, ionic compounds, so a compound is supposed to be an electrically neutral substance, but compounds are composed of anions and cations. So the total positive charge has to equal the total negative charge when you're creating ionic compounds. The cation and the anion's charges have to balance each other out. So for example, sodium ion, which is +1, will bond with chloride ion, which is -1. Mg2+ can bond with oxygen ion, oxide, that's called, because they are both charges of 2. But if you take calcium and combine it with fluoride, calcium's +2, you actually need 2 fluorides to balance out the charge on the calcium. So that's what we mean by the total positive has to equal the total negative charge. They have to be electrically neutral, so you want to adjust the ion quantities in order to make that happen. These ions are held together by what we've learned are called electrostatic attractions, opposite charge attractions. So the calcium ion donates its electron to the fluoride ion, or the calcium atom donates its electron to the fluorine atom and becomes calcium ion and fluoride ion. And then those two are attracted to each other. And typically you're going to see cations as a metal, anions as a nonmetal, or a polyatomic ion. And the next slide is going to show you what I'm talking about in terms of a polyatomic ion. So here are some common ions that you are going, well, you're not going to use all of them, but you're going to use quite a few of them this year. The ions that we are going to commonly use, you will find on page 407. I'm going to really encourage you to memorize those ions because we use them a lot. And if you have to look up the ion formulas all the time, it's going to take you a long time. You're not going to get tests and quizzes finished if you don't know your ions. If you are using, if you're doing any sort of assignment that has ions in it, you can use page 407, or you can use a more extensive list of ions that are in your appendices of the binder. Don't, however, use the appendices in the binder to memorize the ions, because there's a bigger list there than what you have on page 407. So 407 are the ions that we commonly use and we want you to know. So if you take a look, you can see the cations, for the most part, are single atom ions. There's one exception. If you look, ammonium is a polyatomic ion, poly, many, atom. Okay, so there's 1 nitrogen and 4 hydrogens, all with this whole group has a charge of +1. So a polyatomic ion is really a group of atoms that overall has a charge. So there's only one common cation, ammonium, that you're going to need to know, but there's a lot of polyatomic anions. And here's just a few of them. Some of these you don't need to know. You don't need to know the arsenic ions or the silicon ions. But some of the other ones you do. We use carbonate and bicarbonate a lot. Notice that they have CO3 and HCO3 with charges respectively. So you're going to get very familiar with these ions, but we have monatomic ions, just 1 atom ions, and then we have polyatomic ions. And again, that's a group of ions. They're actually covalently bonded. These atoms in the polyatomic ions are covalently bonded together, but that whole group just has extra electrons, or in the case of ammonium, is short electrons. So let's talk about what happens when we form ionic compounds. So initially, you know that the cation and the anion come together, they transfer electrons, but now that you have these charged ions, you can have a cation attracting any other anion around it. And likewise, an anion is going to attract any other cation around it. So the result is this big conglomerate of alternating cations and anions that we call a crystal lattice. So here's actually what sodium chloride looks like. You see the purple represents the sodium ions, the green, no, I guess the purple represents the chloride ions, the green represents the sodium ions. And you've got alternating cations and anions, creating this crystal lattice. So there's an attraction between each of these pairs of atoms. So regardless of what atom donated its electrons to what atom, as long as you have a plus and a minus charge, they're going to attract other pluses and minus charges. So you get this crystal. So this is what sodium chloride looks like. If we had a big chunk of it, if you think about what it looks like when you pour salt onto a steak or whatever you're going to pour salt onto, it's really tiny little crystals of this, but they're very cubic. So sodium chloride creates this cubic structure that you see. Not every ionic compound creates a cubic structure. The shapes are a little bit different in crystals. There's actually entire courses in college that you can take on crystal shape. But here's one of the typical ones. Sodium chloride is a cubic kind of shape. So just to see it visually, I've got this little blurb in here so that you can see the crystal lattice kind of turning.
In summary, ionic compounds exist as giant ionic lattices, not as single molecules. The giant ionic lattice is a regular repeating 3D pattern of alternating positive and negative ions. The electrostatic attractions holding the structure intact are very strong.
And we're going to pause it there because we don't really want to look at properties. We just want to look at the structure. So,
in this account,
so continuing with our look at these ionic crystals, because we have alternating patterns of cations and anions, we don't ever talk about having ionic molecules. We only ever say that we have ionic compounds because they don't have a molecular formula. They have what we refer to as a formula unit. And that is the lowest whole number ratio between the cations and anions in the crystal. So for example, sodium chloride is 1 sodium to 1 chloride. Calcium fluoride, what you saw, was 1 calcium to 2 fluorides. So the formula that we write, that you're going to learn to write for ionic crystals, is really called the formula unit. It's not a molecular formula, even though we say that a lot. It's really not a molecule. It's really a huge crystal of alternating cations and anions. So the crystal literally is composed of moles worth of cations and anions, not just one individual cation or one individual anion. So here's another substance, calcium fluoride. You can see here the big ones represent calcium, the little ones represent fluorine. If you were to count, you would find that for every 1 calcium, there are 2 fluorides, because that's the formula. This creates a more oblong crystal. So if you look at this, you can see these crystals are more rectangular than cubic. So depending upon how the ions pack within that crystal, you get different shapes. But regardless, the formula unit for calcium fluoride is CaF2, 1 calcium ion for every 2 fluoride ions. So you're going to learn soon how to write the formulas for ionic compounds based upon what their charges are and making sure that those charges will neutralize each other. All right, so the last idea we're going to take a look at is the idea of lattice energy. So we have this crystal lattice. Well, there's energy associated with the crystal lattice because there's energy associated with all the bonds within the lattice. So, like I said, energy is associated with the crystal lattice, and we call it appropriately lattice energy. So when a crystal forms, lattice energy gets released. Excuse me. Now think about why. When you're creating that crystal, the cations and anions are gravitating towards each other, they're attracting towards each other, they're creating this stable, very stable, strong arrangement. So it makes sense that energy gets released because we're making something more stable. Think about the electron cloud when we were learning about emission spectrum. The stable situation, the ground state, was when the electron had low energy. The electron would jump to a higher energy level when it absorbed energy. That's when it was in its excited state. In order to come back down to a lower energy level, it releases that energy. So a crystal lattice is actually a low point of energy. So in order to create that crystal lattice, extra energy had to be released in order to form those attractions. Which means the opposite is true if we break a crystal apart. You're going to have to add energy in order to break those attractions apart. Think about separating two magnets. Two magnets are attracted to each other. It takes a little bit of force to separate them. Well, the same thing is true here. To break that crystal apart with the attractions between the cations and anions, it's going to take some energy to do that. So each ionic substance has its own unique crystal lattice energy value that's controlled by our old friend Coulombic attractions. So do you remember what the two characteristics are that control Coulombic attractions? Hopefully you do. Two factors are going to be this, in this case, the size of the ions, not the size of the atom, but the size of the ions. Do we have big ions or little ions? And then also, what's the charge on the ions? And charge is actually going to have a bigger impact. So when you were doing the introductory activities, the POGIL and so forth, to Coulombic attractions, you were asked to create some general equations that represented how energy changes with these two ideas. And so here is what we call Coulomb's law. Coulomb's law actually takes those ideas and puts it into a chemical equation, a algebraic equation. So the energy of the crystal lattice energy, is equal to the product of the two charges divided by the distance. So bigger charge, bigger force, bigger distance, smaller force. So those, you've learned these ideas already when we were learning about periodic table trends and why some things lose electrons easily and so on and so forth. The other thing in here is a constant. In order to set these things equal, we have to use a constant. Now this energy is going to change depending upon what the ions are, because different ions have different charges and different ions are different sizes, so the distance between them is going to increase and decrease. So that's pretty much the ideas about an ionic crystal or ionic compounds that we want you guys to know in terms of the structure. It's a pretty simple structure, alternating cations and anions that are attracted to each other, either strongly or weakly. That strength of attraction you are going to see is going to control a lot of things that we look at in terms of properties of ionic compounds. One thing in particular, solubility. The strength of the crystal lattice is going to control whether or not that crystal will dissolve in water. And we are done.